And greetings, welcome to the Evidence Reasons Academy. I'm sorry. Greetings to Godzilla Freak, long time no see, and greetings Paleo Logos. Let me just type in a greeting to you. Uh, this is going to be a nerd out session, and I didn't have a lot of time to prepare a very careful show. So, um, since this is an academic channel, we'll be kind of just doing this like a homework session, not like something that's really polished at all. If you're wondering what's behind me, that is the Major League Baseball playoffs. It's the San Diego Padres versus the LA Dodgers. I usually root for the underdog. Way back in the day, I actually rooted for the Dodgers when they were playing the Oakland A's in the World Series. I got to see the famous home run in the ninth inning with Kurt Gibson hitting the home run with 2 outs, 3 balls, and 2 strikes, and he was just hobbling. Dennis Eckersley pitched a backup slider, and Gibson was sitting on it, and he just hit it out of the ballpark. So I really wasn't much into baseball, except I'll watch like the big games, and my mother loved it. And so just to keep her company, a lot of times I would just sit and watch with her. And that was a very precious time in our family. When Dad was alive, it'd be me, Mom, and myself, and we would watch the Washington Redskins football. And that was a real blessing to the family to kind of help keep us together. Sometimes we went through rocky times. That was the one thing that unified us. And I thank God for that. So even something as trivial as that. So hope it's not too much of a distraction. I think the Padres are ahead 1-0. And so like I said, I'm rooting for the underdog. So the question today is, let's just back up to some questions that have troubled people. Is there a does time really change the faster you go? Does it change depending on the strength of the gravitational field? So the question about general relativity deals with the effects of gravity and velocity. Special relativity deals with the effects of velocity. And time, one thing that is very important is that the claim is time flows slower when you're moving fast. That's special relativity. Now, there are some people that are objecting to that, partly because quantum mechanics, if I could show this to you, just so you know I'm not making this up, I'm going to show the time problem. Let's see if I could find it. The problem of time. So I'm going to share my screen here. The problem of time. So it is in Wikipedia. And this will lead to where I'm going to head to. So I studied physics at Johns Hopkins, and I'm trying to always relearn it. So let me just read this. This is the Wikipedia article. In theoretical physics, the problem of time is a conceptual conflict between general relativity and quantum mechanics, in that quantum mechanics regards the flow of time as universal and absolute, whereas general relativity regards the flow of time as malleable and relative. So just keep that in mind. I'm not, I wanted to just reference that to say I'm not making this up. Now, it said they need an expert physicist to comment on this in the article. Sabine Hassenfelder, who's a theoretical mathematical physicist. She has a big YouTube following. She has said she has said general relativity cannot be quite right. And she cited the problem of time. So, and yet, when we, for example, when we have um, like spaceships or GPS satellites, we do know that there is an apparent time difference that was predicted that we measure that is also consistent with the predictions of general and special relativity. One of the examples of there's a famous some of the early experiments on this was the Heffel-Keating experiment, Heffel-Keating, where they took, let me show it to you, just to kind of make this a little bit more concrete. The Heffel-Keating experiment was a test of the theory of relativity. When they say the theory of relativity, among the initiated, it would mean the general theory. So the general theory includes the special theory. So general relativity is acceleration and velocity. Special relativity is velocity only. In 1971, Joseph C. Heffel, a physicist, and Robert Keating, an astronomer, took 4 cesium beam atomic clocks aboard commercial airlines. They flew twice around the world, first eastward, then westward, and compared the clocks against each other that remained at the United States Naval Observatory. When they reunited, the 3 clocks were found to disagree with one another, and their differences were consistent with the predictions of special and general relativity. So how do we account for the clocks being different? Did time flow different? So they have these things called kinematic time dilation, that's velocity dependent, and gravitational. And here are the results, just as a cute so there are more experiments that followed, and then definitely we would not have the accuracy in GPS if we did not have this. So pretty much everyone's accepting there is a phenomenon. And let me see if there was a cute observation here. Heffel and Keating obtained $8,000 in funding from the Office of Naval Research for one of the most inexpensive tests ever conducted of general relativity. Of this amount, $7,600 was spent on the 8 round-the-world plane tickets, including 2 seats, one on each flight for Mr. Clock. They flew eastward around the world, ran the clock side by side for a week, and then flew westward. The crew of each flight helped by supplying the navigational data needed for the comparison with theory. In addition to the scientific papers published in Science, there were several accounts published in Popular Press and other publications. So one of the cute things about this, just in my opinion, what a nice way to do an experiment. You get to travel around the whole world. I think that would be, that's a dream, I think, if I were a physicist, professional physicist like that. So, hats off to them for pioneering this work. And I think there were a lot of indications this was correct. So now we have this time problem. Quantum mechanics wants an absolute clock, and yet we're having these measurements. So an absolute time. How do we reconcile that? Well, some people have suggested there is an absolute time. I don't want to put words in Philip Dennis's mouth, but my understanding, he's a young Earth creationist, but also a secular scientist that specializes in special and general relativity. He and I together have been very critical of Jason Lyle's asynchronous time convention or something like that, not the inability to measure the one-way speed of light. I have vigorously argued that you can measure it, and so has Philip Dennis. I think Philip Dennis has said he believes in an absolute clock, or an absolute time. There's absolute time. I'm sorry, absolute time. But I think the effect we're measuring, that we're seeing, is the clock slow down. That is one way to reconcile this. How can you reconcile general relativity and also special relativity with quantum mechanics as far as the time? Well, one way to do it is to assume maybe what we're measuring is some effect that is happening on the clock based on velocity or gravity. And I think that's more reasonable. So this is going to be kind of funny because the mainstream will say time flows differently, and yet they don't exactly say that because of quantum mechanics. So I'm just saying, depending on how you read it, there's just confusion factors that abound in this. Now, what is not at this point in doubt is the clocks will register different amounts of time. So either time is flowed differently, or there was some effect that speed and gravity have on the ticking of the clock. I think it's the ticking of the clock. I think there is absolute time. And Philip Dennis has also pointed out there is, some of this thing about space-time is just a mathematical construction. It is not physical reality. It's just a conceptualization. You can build space-time for a lot of things, including the movement of sound through a medium like water. And you can have all these cone diagrams or whatever. And I was really impressed that he said that, because I actually got that independently from Cahill. So I'm going to say that we have experiments, we have the equations, but there's some disagreement on what it means. And then also some of the classic things in standard textbooks, we have to look at it a little bit more carefully. That being said, I'm going to try to be careful when I say what I describe as mainstream versus something I'll add that's non-mainstream. So most of this will be mainstream stuff. So how did this all come about prior to Einstein? Before Einstein, the idea that time, that there was a slowdown in the clock, or the time flowed differently, was already being derived by Hendrik Lorentz. So there is, in fact, when they teach special relativity, there's something called the transformation that's the Lorentz transformation. It's like, why isn't the Einstein transformation that does all this, the changing of time, what they call time dilation? It's because I think the Padres scored a home run. Sorry, I just noticed them giving high fives. The Lorentz transformation. Let me see, peaceful science, Lorentz. The equations were already set up before Einstein, and I don't think Lorentz got enough credit. He still won the Nobel Prize. And historians know how important Lorentz was. And so I just have some photos here I'd like to share. These are the individuals who made physics, modern physics, just tremendous. I think that's Max. I mean, there's Max Planck, there's Schrodinger, there's Dirac, there's Einstein. Here's Einstein. Here's Lorentz, Madame Curie. De Broglie, I think, is there. Schrodinger, Bohr. I mean, all the names you'll see in modern physics textbooks. And you could see, Einstein's in the center because he's, I think that was not accidental. They wanted to revere him. and say he's he's kind of the heart of modern physics. To his right, and I think that is symbolic, is Hendrik Lorentz. And so we have two conferences. Someone with a lot of money wanted to bring them all together. There are pictures of Einstein and Lorentz walking together. So what is the big deal about? It is this. It is, let me see. It is this equation right here. See if I can highlight it. You see it right there? Gamma equals 1 over v squared minus c squared. C squared is the speed of light. V squared is the velocity of, like, say, a spaceship or whatever. And this will lead to how in the mainstream, what they call how much time will slow down. So if you go to 0, let me look at this. No, if you go to very close to the speed of light, time will slow down by a factor of gamma. So a bazillion ticks in kind of a stationary frame, it'll only be like, okay, so let's just use the Bible verse. A day is like 1,000 years, and 1,000 years is like a day. So it might be 1 day on the fast-moving spacecraft, might be 1,000 years on a stationary place, relatively speaking, like the Earth. Earth isn't strictly stationary, but it's because it orbits the sun and it's rotating. But relative to this hypothetically fast-moving spacecraft that's 99 point some percent of the speed of light, a day on that spacecraft is like 1,000 years on the Earth, and then vice versa. 1,000 years on the Earth is like a day on that spacecraft. And so the Lorentz transform will tell you how fast you have to go to make a day equal a day on the spacecraft be like 1,000 years on the Earth, and vice versa. And the Hefel-Keating experiment, plus many, many others, have confirmed this relation. As far as we know, it's good. So thank you. God bless you. So I was relating this equation here to the Bible, where it says a day is 1,000 years and 1,000 years is as a day. If you have very high velocity of your spacecraft relative to the people on Earth, 1 day on the spacecraft will be like 1,000 years on Earth, and 1,000 years on Earth will be like 1 day on the spacecraft. So we have a hypothetical example that if you're going that fast, the way it's described in the Bible can be seen in this way. Although I think that's probably a poetic passage in the Bible, but I hold out that maybe this is something the Lord was also trying to let us know, that this is the way physics works. It's speculation, that we do see it. So how did Lorentz come up with this? I mean, that wouldn't be anything. I mean, that, it just sounds like science fiction. How would you just come up with that? You go real fast, and 1 day your time will be like 1,000 years on Earth. So let's say you took off on a spacecraft and you're just going so fast, a day of your life on the spacecraft would be like 1,000 years on Earth. So that's what they call the twin paradox. If you had two twins, one of them that flew on the spacecraft, the poor guy that's left on Earth will have been very elderly, the guy on the spacecraft would hardly have aged. How could Lorentz have come up with this? So as I've tried to study the question historically, so Lorentz was coming up with this in the late 19th century, which is about 150 years ago. They were just discovering, formulating electromagnetic theory. And as he studied it, he began to, as Maxwell was creating these equations and Lorentz was examining the experimental data and pondering all this, the community was beginning to think of this possibility. And I'm going to try to derive that from Maxwell's equations, where you could see that the way Maxwell had written the equations, it would predict that. So why would we suppose this? Let me look this up. Permittivity. So there's this thing called permittivity. It's a property that is important to electric fields. So let me just read this, and I'm just going to scan it. I'm learning this along with you, by the way. In electromagnetism, the absolute permittivity, or simply called permittivity, and denoted by the Greek letter epsilon, is a measure of the electric polarizability of a dielectric. The polarizability of a dielectric. A material with high permittivity polarizes more in response to an applied electric field than with low permittivity, thereby storing more energy in the material. In the electrostatics, the permittivity plays an important role in determining the capacitance of a capacitor. Measure of electric polarizability. More generally, in the simplest case, the electric displacement field D, resulting from an applied electric field, is D equals epsilon E. More generally, the permittivity is a thermodynamic function of state. Whoa, I didn't know that. It can depend on frequency, magnitude, and direction of the applied field. The SI unit for permittivity is the farad per meter. The permittivity is often represented by the relative permittivity epsilon r, which is the ratio of absolute permittivity E to the vacuum permittivity epsilon naught. I was looking in my electromagnetic theory book for that, and it's so nice to see it summarized here in my book. The dimensionless quantity is often ambiguously referred to as permittivity. Another common term encountered for both absolute and relative permittivity is the dielectric constant, which has been deprecated in physics and engineering as well as in chemistry. Deprecated meaning we're trying not to use it so much anymore. It's a term out of favor, but I still hear the term dielectric constant. Okay, so that Wikipedia entry is like for today. This is my book from 30 years ago. And I think they still, let me just see, let me peek. Yep, page 136, dielectric constant. So that's the dielectric constant. All right, permittivity. So vacuum permittivity is this number. And let's see some relative permittivities. I'm just for the benefit. Okay, so this is trying to set this up for where we're headed with. Okay, this is still a long path to figuring out why Lorentz said, a day's, figuratively speaking, and I don't mean to put words in his mouth, I'm just saying metaphorically, a day is like 1,000 years. How could he come up with that based on electromagnetism? So the permittivity, all these materials here can have different permittivities. So we have air, which isn't much, and then there is mica, and then methanol, ethylene glycol, ammonia. Okay, so why would this be at all of interest? Well, for you electrical engineers out there, you deal with things called capacitors, and capacitors are used to, how does that work? High frequency AC can get through a capacitor. It's a high pass filter. It's been a while. Okay, guys. I think an inductor is a low pass filter. Something like that. Okay. So, Ben Rex, correct me if I'm wrong. So when we were building filter circuits, passive filter circuits in electrical engineering, so like when we were building radios, that would help us, and then it helps with the way we build audio equipment. Capacitors were useful. It got even better when we added vacuum tubes, which we called helped us do what we call active filtering. And then now with transistors and everything, it's just fabulous what we've been able to do. But capacitors were very important, and so that's why we had permittivity. So how does this relate to relativity? Ideally, I guess it was just, and again, I don't have all the historical documents. I'm just seeing little clips here. So what I'm about to say may be inaccurate, but I think it's probably close enough. It would be desirable to think that however we measured vacuum permittivity, it would be the same no matter how fast you were going. You would expect the capacitor to work the same way, whether you were traveling, you're stationary or moving close to the speed of light. So if you're on that spaceship, you'd want all your electronics to work the same way. I think that was kind of the intuitive motivation. There were probably I've heard that there are more subtle things like that, but let's just suppose that we would want that. So the first postulate by Einstein many years after electromagnetic theory started to be accepted was that the laws of physics are the same in all reference frames, meaning whether you're stationary or going fast. And there's going to be a subtlety as to what you mean by stationary versus fast. It has to deal with acceleration, and it leads to an interesting problem whether there is an absolute reference frame, which I will argue there is. Some people will deny it, and I'm just like, well, it's undeniable that one clock is ticking faster than the other. That implies a preferred reference frame as far as velocity. There is an absolute zero of velocity. So so you have this this desire that, let's say, for a lot of things, a lot of the behaviors of physical systems will be identical, independent of your reference frame. Unless you begin to apply accelerations, you'll start to see a difference. Okay, so Einstein's postulate was simply stated, laws of physics the same in all reference frames, meaning whether you're fast or slow. I'm going to add, it depends. It'll differ a little bit if you start applying accelerations over time. And this is going to be interesting. So let me just say, let's go with most of the laws, okay? So that this measured permittivity will be the same across all reference frames. So there's a consequence for that. Maxwell, James Clerk Maxwell, let's just look at the history. There's a history of Maxwell's equations. So the work was done by Maxwell, published from the 1850s through the 1870s. And it was verified by Heinrich. A lot of it was verified by Heinrich Hertz in the 1890s. There were 20 equations that were synthesized to 4. Okay, let me read this. Oliver Heaviside studied Maxwell's A Treatise on Electricity and Magnetism and employed vector calculus to synthesize Maxwell's over 20 equations into the 4 recognizable ones which modern physicists use. Maxwell's equations also inspired Albert Einstein in developing the theory of special relativity. And that's what we're trying to do today, how it was inspired. Okay, the final form of Maxwell's equations was published in 1865, A Dynamical Theory of the Electromagnetic Field, in which the theory is formulated in strictly mathematical form. In 1873, Maxwell published a treatise on electricity and magnetism as a summary of his work on electromagnetism. In summary, Maxwell's equations successfully unified theories of light and magnetism, which is one of the great unifications in physics. Amen. So, say 1865, 1873. I mean, this is hard work. So going back to Maxwell's equations, speed of light. So now let's actually look at the modern form of Maxwell's equations. And we've been covering Maxwell's equations on this channel, first starting with multivariate calculus. So I'm sorry, let me get this bigger. So the speed of light is 1 over epsilon naught, which is the permittivity, time the square root of epsilon naught times magnetic permeability, which is mu naught. But just note, it's desirable no matter how fast you're going that you want epsilon naught to be measured the same way. So the thought is, at least as far as your personal experience, if you're traveling fast in this hypothetical spaceship, all your electronics are going to work well relative to the way you're experiencing things, as if you weren't moving so fast. So let us, for completeness, look at magnetic permeability. And I'm not very familiar with that, even though I took electromagnetic theory. Magnetic permeability. Magnetic permeability. In electromagnetism, permeability is the measure of magnetization that a material obtains in response to an applied magnetic field. Permeability is typically represented by the italicized Greek letter mu. The term was coined by William Thomson, first Baron of Kelvin, in 1872. This is amazing because Maxwell's equations was not till like 1865, 1863, and used alongside permittivity by Oliver Heaviside in 1885. The reciprocal of permeability is magnetic reluctivity. Reluctivity. The SI of permeability is measured in henries per meter, or equivalently newtons per ampere squared. Newtons per ampere squared. The permeability constant, and by the way, Newton is kilogram meters per second squared. Okay. Also known as the magnetic constant or permeability of free space, the permeability constant mu naught, is the proportionality between magnetic induction and the magnetization force when forming a magnetic field in a classical vacuum. Let me just, okay, in the macroscopic formulation of electromagnetism, there appears two different kinds of magnetic field. The magnetizing field, which is generated around electric currents and displacement currents, and also emanates from the poles of the magnets. The SI units of H or amperes per meter. The magnetic flux density, which acts back on the electrical domain by curving the motion of the charges and causing electromagnetic induction. The SI units of B are volt seconds per square meter, or Teslas. The concept of permeability arises in many materials in vacuum. There's a simple relationship between H and B at any location or time, in that the two fields are precisely proportional to each other. B equals mu H. Where the proportionality factor mu is the permeability. Let's just read a little further. The permeability of vacuum, also known as the permeability of free space, is a physical constant denoted mu naught. The SI units are volt seconds per ampere meter, equivalent to the Henry per meter. Typically, mu would be a scalar, but for anisotropic material, mu could be a second-rank tensor. Ouch. Okay, now I'm getting a headache. However, inside strong magnetic materials such as iron or permanent magnets, there's typically no simple relationship between H and B. The concept of permeability is then nonsensical, or at least only applicable to special cases as unsaturated magnetic cores. Not only do these materials have nonlinear magnetic behavior, but often there's significant magnetic hysteresis. That's hard to explain what hysteresis is. I think it's like kind of the changeability of the magnet. So there's not even a single valued functional relationship between B and H. However, considering starting at a given value of B and H and slightly changing the fields, it is possible to define incremental permeability. Okay, this is now getting really nasty. Relative permeability is the ratio of permeability of a medium to the permeability of free space. So let's look at the table of relative permeability. See if I could relative permeability. So copper is actually less than free space, which is funny. Ferrite, nickel, and zinc is 640. Stainless steel is 1800, up to 1800. Hydrogen is 1. Okay. So it's not quite right to say permeability is absolute, the lowest you can get is 1, because for some reason copper has lower. But the idea is, no matter how fast your hypothetical spaceship is going, and you have a permeability measurement, you want your electromagnetics, your magnets, your generators, your motors to work the same way inside the spaceship, no matter how fast you go. And then you want your capacitors to work the same way. And so it's like, well, that's really reasonable if you're flying real fast. But it resulted in something kind of funny. What do you have to trade to make that work? Because what that would mean is the speed of light would have to be constant. Your measured speed of light would always be constant, wherever, no matter how fast you're going, whether you're stationary, quote unquote, on Earth. You're not really stationary, but relatively speaking, or whether you're traveling in a fast spaceship, you would want epsilon naught and mu naught to always be the same. But that has the consequence of the speed of light being measured the same, independent of your reference frame. So this, reference frame being whether, like, say, you're on Earth or in a spaceship. What does that? It has consequences. It would mean, again, like a day would be 1,000 years, like a day on your spaceship would be 1,000 years on Earth. With that, and that seems outrageous. But again, we have all these experiments that seem to confirm that. So now what do we do? In the modern day, some people have been saying, a very small minority, and I think the minority this time is right, that it's not that time flows differently, it's the clocks slow down. So when you're on that spaceship, all the clocks, everything, all the molecular processes just get very, very slow. And so it's not that time flows differently, it is the fact that your clocks slow down. Well, that's the math we're trying to show. So let me see. Or I bet there is someone who did this. Lorentz, let's say time dilation, day, 1,000 years. Okay, it says here, in what circumstances, someone asked this physics question. In what circumstances would 1,000 years on Earth be a single day? And that's not, it's supposed to be, what would be, in what circumstances would 1,000 years on Earth be a single day? And so you get it here. You would have to be traveling, if your spaceship could travel that value right there, and let me just zoom in so you could all see. If you traveled 99.999999996% the speed of light, and turns around, the ship will return after 1,000 years have elapsed on Earth. And so the question is, in what circumstances would 1,000 years on Earth be a single day? So this is the prediction of special relativity. Since we don't have spaceships that go that fast, we have to go with something far slower, such as satellites, GPS satellites. We see a small effect to that, and it's measurable. We have to make that adjustment so that we will be able to get precise GPS locations. If we didn't make that, our GPS would not be as accurate. So this is important practical consequences of the Lorentz transform. But if we extrapolate it out to that, you could see physicists have pondered that, going to that verse in the Bible. Actually, I think it's in two places. The New Testament in Peter, quoting something in the Old Testament. So there you have that relation, and it's based on the presumption you want your spaceship to behave the same. A lot of the stuff happening inside your spaceship is going to be constant, independent of your speed, which is very reasonable. But the trade-off is that you get these funny effects of the clocks synchronizing differently versus being stationary versus being on a very fast spaceship. And not that I think we'll ever be able to build spaceships that can travel that fast, but if there's any object moving in relation to the Earth, assuming the Earth is relatively stationary, and I'll argue that it is, if that object is moving like at that figure of 99.999%, the speed of light, 1,000 a day on that object is like 1,000 years on Earth. Oh, we're actually coding. Okay. One thing you might relate to, thank you for boosting my counts. Don't worry about it. I'm actually, let me write you a note here. It's so great to see you. I got to tell you something here. Thanks for dropping in. I'm going to type a note to you. So in his image writes this. He's trying to boost my views. And in his image, I'm actually proud to have so few views. That means the viewers are part of a very elite club. So there you go. So in what circumstances would 1,000 years on Earth be a single day? And Dr. Joel may have watched the early part of this. He said, no, not the Kirk Gibson home run. Was watching, not there at the time. Lifelong Padres fan. Great Guardians win over them Yanks today. Yes, I didn't know about you mean the Cleveland Indians? Yes, happy about that. Kirk Gibson's home run was over the Oakland A's, not over the Padres. But I'm rooting for the Padres tonight. So anyone want to update me on the score? I see it is 2-0, and I can't see what inning it is. So I was just updating on everyone on what we're trying to do here. And this is also, there is a saying, if you want to learn something, you try to teach it. And that's what I'm doing here. Let me just try to reduce some of my number of windows because I have so many open. Goodness, I have so many of these open. Permittivity. Maxwell's equations. All right. So if we're going to try to invoke kind of a variation of Einstein's first postulate, when you have a very fast spaceship or anything else moving relative to another, you'd want all of your processes to work the same way, like your capacitors, your inductors, your motors, your generators, etc. But that would have consequences of requiring the speed of light to be the same measured in each reference frame, whether you're inside your spaceship or you're on Earth, stationary. but this would lead to very strange effects. When you work out the math for that to be true, you would have to have time flow different, or as I will say, the clocks are different. So the clock speeds are different. Greetings, long time no see, brother. So we got the whole gang coming out of the woodwork here. Great to see you all. So now the agony part. I spent an hour setting up why you would get this phenomenon of time differences. Just using kind of common sense, it leads to really peculiar results that we've, again, covered experimentally. But how do we demonstrate this mathematically from Maxwell's equations? Maxwell probably was, not too sure about the idea from what little I've read, like second, third, fourth hand, that he didn't think this would apply to very high velocity type things. And so this question still, there's a lot to go through this to see the consequences. So he wrote the equations. Some people have said that, he said it needed some correction because it would lead to kind of funny consequences. It was definitely confirmed by both experiments and theory. So let's go now to the agony part. So I'm going to go for, let's see, how can I do this? I need to open I'm going to open a Word document. Let's see if I could open a Word document. One moment. And let me do that. I'm going to try to open a Word document, and I'm going to also open up some of my work on this at Peaceful Science, or what I call Pitiful Science, Pitiful Pseudoscience, run by Joshua Swami Das. So let's take a look. Because I have to do this thing, what they call using latex formulations. So now it's going to be now we're getting to the agony part. Okay. So now let me grab, I want a Word document. So I'll start with a new blank document. And Peaceful Science, Lorentz. So now we're going to go to the difficult stuff. Okay, so now let's walk through this. So we talked about the permittivity and the permeability. You get the speed of light. You want this for a variety of reasons to be constant in all reference frames, whether you're stationary or moving. But then you have some consequences. What would happen? There is this okay. So we saw Maxwell's equations stated. Let me just, for reference, let me show them off again. Hang on. And we've been actually crawling through Maxwell's equations on this channel because I'm trying to revisit electromagnetic theory. And this is what Maxwell's equations would look like. Oh, I need something bigger than that. Come on, give me something bigger. Okay, that's bigger. So that's Maxwell's equations of electromagnetism. Maxwell's equations, it's actually easier to understand the differential form. And we went over the divergence formula. And then when Dr. Russell Humphreys was here on Wednesday, we went over curls. So E stands for electric field. B is traditionally the magnetic field. Q is the charge. And then we have these terms epsilon naught, which we talked about, and then mu naught here. So this is the electric permittivity and magnetic permeability. And then when you put all this together, one of the consequences is the speed of light is 1 over the square root of epsilon naught times mu naught. But there are other things that Maxwell's equations predict. And let me get rid of this because we don't need this. One other thing that Maxwell's equations predict, and I had this on my Peaceful Science website, is this. This is the equation that describes why the nature of light. It is changing electric and magnetic fields. So you hear the term a lot, electromagnetic waves. Electromagnetic waves. So light has a wave and particle nature that we know, we know that through quantum mechanics now. But in the 19th century, we were studying the wave nature of light. It is a wave of electric fields, changing electric fields, coupled with a wave of magnetic fields going through space. And that was, Maxwell's a Christian, probably a creationist. It was beautiful that he discovered this. This was landmark. He showed that light was composed of electric and magnetic, changing electric and magnetic fields. The thing that was, Maxwell collected a lot of equations from other people, like Gauss. These are Gaussian type equations. This one is Faraday's equation. Michael Faraday, who was also a Christian, probably a creationist. And then this is Ampere-Maxwell. So what this does is it shows, so you see the term E and the term B, magnetic fields changing over time create electric fields changing over time. Plus a little bit, the J is what they call a displacement current. And so this is kind of beautiful, trying to understand the nature of light in terms of magnetism and electricity. This was landmark in many ways, and kind of in, I would just say, as a philosophical, theological rumination. The key to understand, I think a lot of creationism will advance as we understand the nature of light. So the metaphor of light is used a lot in the Bible. And in terms of physics, the understanding of light is key to understanding a lot of physics. It's just beautiful. That was a very apt choice by our Lord to use the word light as a metaphor, because in physics, we understand a lot as we understand light. That's why Maxwell's equations are so important. So going back to these equations, this one tells us changing electric fields create changing magnetic fields and vice versa. And it's kind of complicated to explain, and I will just take it as an axiom, not as an axiom, but something that someone else derived, that the relationship of the changing electric and magnetic field, or the changing electric field in relation to how it changes over time, and then also how it changes in terms of the location, is described by this. This is called the electromagnetic wave equation. It is a solution. So for those who understand differential equations, this equation is a solution to the differential equations here. I don't know if specifically it's a solution to all four equations or it's just the fourth equation, That's something to ask a mathematical physicist. So just to review, you have differential equations, and then you have solutions to differential equations. Real simple example for ordinary differential equations, f equals f prime is a differential equation. It relates a function to its derivative. Solutions to that would be c of e to the x equals f of x equals f. That would be a solution to that differential equation. If it's single variable, it's a ordinary differential equation. If it's multivariable, and Maxwell's equations they are partial differential equations, and they are partial differential equations, first order partial differential equations. So let's kind of move on as we derive this agony. So I'm going to try to save this here. Let me see if I can save it. Show as text commands. And this is where it gets a little scary, guys. I'll show you how I had to type this in to render it. I want to lift it out of the pitiful pseudoscience website of Swamidas. So I can write my own document. So let's see, insert equation. I ought to be able to insert this. I don't know why I can't insert it. I ought to be able to do this in LaTeX. Agony. Another aggravation I'm going to have to deal with. So we have MathJax. Where did I see that? MathJax equation source. Okay. So let me try something else. I'm going to have to get this working. LaTeX run viewer. So if I put something that looks like this, let me show it to you. This is really scary. If I want to write an equation like this, I have to type it in like this, which is really scary. I mean, I got to tell you, I had to figure out, I started to think in the LaTeX language. Not only is the math language bad enough as it stands, I had to translate it to LaTeX. So LaTeX reads like this, and then the mathematical symbols look like that. And after a while, I just start to think in both languages, and that's kind of scary, honestly. Your mind starts to really get stretched. So what I'm going to do is I'm going to save all these equations into a document. And I'll know that that's the electromagnetic theory. That's the electromagnetic wave equation. So that describes the wave flowing through space. That describes the electromagnetic wave, the photon, the wave nature of the photon flowing through space. Okay. So classical electromagnetics, which is what we're doing, electromagnetism, does not deal with the particle nature of light. It has the wave nature of light. So now let's go a little further. We can also, let me see, I could do the derivation here. One way to frame this, and there, I wish I could just, I need to ignore some of these guys. They're just nasty people. I'll do that later. Let's see. We can, I'm looking for the alternate formulation here. There's a Heffel heating experiment. Okay. I don't have it explicit here, guys. I'm just going to have to go to this. I'm sorry. One moment. I'm sorry to be just fumbling through this. This is kind of complicated, needless to say. So one way we can frame this is we could also say, okay, so this is the Laplacian, this del squared, the Laplacian of the electric field equals mu times epsilon, mu naught times epsilon naught times the second order derivative, partial derivative with respect to time of the electric field. Alternatively, if you subtract mu naught epsilon naught from both, and then just make this del squared and this partial derivative an operator, you can alternatively frame this that way. And I'm going to save that. Text command. What's the text? Oh, I don't like that. Let's look at the. It would be that. So I'm going to store that. This is great. I can store all this. Let me save this somewhere. This would be under. So this equals 0. So by the way, this equation here was solved by guys really, really smart. So I'm just using that as a starting point. How that could be derived, I'm not even going to attempt. That would take me years. So that is a solution to Maxwell's equation. And it basically said, you can have these nice sine waves floating through space. These nice sine waves traveling through space, which is beautiful because it will resemble sound, a sound wave. Okay. So that was that was kind of like a hard start. And so we would have coordinates x, y, z, say on Earth, x, y, z, and t, the four coordinates, x, y, z, and t. So x, y, z are the spatial coordinates, t is the time coordinate. We would want okay, so when we take the Laplacian, so I'm going to expand this Laplacian right here. What does the Laplacian of E look like? So we take the left-hand part of the equation. Let's look at what the Laplacian will look like. And let me go way down. So I'm going to restate the proof a little differently than the way I laid it out on peaceful pseudoscience, pitiful pseudoscience. Okay. We want, hang on. There. Wait. Yep. Let me go up here. So I'm going to have to do this in 2 screens so you could see a little bit better. And I know I'm going to lose my poor viewers because this is agonizing. What we want, what I'm going to attempt to do, it's easier if I do this in 2 screens. And someday I'm going to polish this up so it's not so clunky. It takes a while for this to update. We're going to take this equation here. Okay, we're going to take this equation. You see the Laplace operator and apply it to E. Now you can replace E with psi or B, it doesn't matter. But I like using psi just for now. I may change the symbols. So we're going to expand this equation here using the Laplacian operator and then the second order derivative and apply it to E, or you could apply it to B, or you could apply it to psi. It doesn't matter. The symbols are really independent of the concept. I'm just going to use psi. Maybe that's a poor choice of symbols, but let's just go with it. So this psi here, this here is the Laplacian, and we covered Laplacians in one of the talks. So this is the Laplacian here, and then this is the second order derivative on psi. So let me just copy this now. And maybe to kind of show what I'm trying to do. I'm going to copy it now to my template. Yes, I can read this. Kind of scary that I'm starting to read this. Okay. So let me just think here. I know what this is, but it's so hard to just render all this. I'm trying to find a way that I could show this on the screen so you could see the derivation. So maybe I'll use the online text editor. Oops, sorry. So we start off with this. And instead of E, I'm going to use psi. Let's see if I could do that. Okay. Okay, psi. And use that. I'd like to use a vector. I need to find a vector notation. Hang on, let me see if I could put the arrow there. I need to find a vector. Because I need to emphasize these are scalar Laplacians being applied on a vector. scalar Laplacian applied on a vector. There it is. Let's see how I show a vector. It is slash vec. Okay, I use the word slash vec and in parentheses. So I would use slash vec and then put this. Good. All right. Slash vec. That's better. Let me save this. Okay, I'm sorry. Let me expand. This is what I wanted. We could start with that. That'll be a little nicer. That's just to make it generic. Let's see. Okay. So now this has the nice vector notation I was looking for. Let me get this back. You see this equation here? That's the Laplacian on that times the second order derivative with respect to partial derivative with respect to time. Thank you for the kind words, brother. Now you know why I watch the baseball game while I'm trying to do this, because this is just really tedious work. So now what we can do is I can add this to both. I could subtract the left-hand side of the equation here. I can subtract this from both sides. And let's see if I can get another line. It's not supposed to do that. Line. Okay. I've got some separation. What I can do is I could do this. Let's see. Wasn't supposed to let me do that. Hang on. It's not what I wanted to do. Cut. That equals 0. All right, so start with this equation. And as I said, that's something that some genius had figured out. Probably took years to figure that equation out. That describes the light wave traveling through space. So this equation describes the light wave traveling through space. Just nice little one of the solutions to this is a sine wave, which is beautiful because electrical engineers love sine waves. It's not apparent from that monstrosity that that's what it's describing, but that's what it is. I've just subtracted this from both sides of the equation and I get that. So since it took me a lot to get to that point, I'm going to put it in my little document where I'm storing all these derivations, and then I'm going to be able to do this a lot faster the next time. So this is just kind of a difficult practice. And thank you, Damien, for hanging with me here. All right, now that we did that, I'm now going to expand. I'm going to take the Laplacian of this. I'm going to expand this out in terms of what that Laplacian means. And to do that, I happen to have it in my document. And it's this right there. Text command. I wish this wouldn't render like that because it's a pain to copy this. now let's go here. Oh boy, it's really not wanting to show this off. Agony. I'm going to find a new rendering tool to do this because this is just getting unwieldy. So this, I'm going to expand this. So remember we covered what a Laplacian will look like. It's just the scalar Laplacian applied to a vector equals there's got to be a better way. Yeah. I'm working on it, brother. I'm sorry about that. The scalar Laplacian applied to a vector is the second order partial derivative with if we're talking about Cartesian coordinates, we go from the second order derivative with respect to x of the vectors, x component, the second order derivative with respect to y for the y hat coefficient, and then the second order derivative with respect to z for the z hat coefficient. And then this here, this here is the same as this. Okay, so I just expanded that equation and I'm going to save this. And then I'll explain what the meaning of all of this is, at least try to. This is good practice for me to figure out how to tutor in math, because I have to be able to do this a lot more efficiently than I'm doing it right now. So now, okay, so what the heck is this describing? This is the sine wave. It would include the sine. I mean, there are many solutions, but let's just say hypothetically a sine wave is one way to represent, is one solution to this. So you have a sine wave going through space. So let me try to show what this would look like, at least conceptually. Give me a moment here. Well, I'm going to say, okay, EM wave. Let's try an EM wave. All right. This is a typical thing you'll see in a electromagnetic theory book. It is unfortunately a little deceptive. So this is the intensity. These vectors here are not physical sizes. They're the intensity of the electric field varying as a sine wave through space. So basically, as the photon travels, the intensity of the electric field is changing, and the variation looks like a sine wave. And then this is the wavelength. So the equation, this monstrosity of an equation here, let me see, the monstrosity of some of these equations here, where did I go? Online, yeah. It is described, that sine wave plus a few other solutions is described by this equation. I mean, this is just monstrous, but it's like, physically speaking, it could represent something as simple as this picture here. Something as simple as this picture here is represented by this monstrous equation here. Okay, so I'm just trying to say, it may look really ugly, but it's really at some level describing something that, really doesn't look all that bad. It's just the math details are just grueling. And so now I'm going to take the next step and show you how we're going to describe the behavior. Okay, so you want that sine wave behaving that way on a stationary reference frame, like say on the planet Earth. Okay, granted, Earth is not exactly stationary, but let's just say its absolute velocity is pretty slow. So you're having the sine wave traveling through space, like or through through a vacuum. If you have a vacuum chamber and you're transmitting light through that vacuum, you would get that sine wave pattern going through there in terms of the intensity of the electric field. Now notice the amplitudes are not physical amplitudes, they're intensity amplitudes. That's why that diagram is a little bit misleading, and I got messed up mentally for decades not understanding the significance of that. It's only now as I studied the math it starts to make sense. And so there's some pitfalls in understanding what's being described. But so what do we want to do? We want to have this, if you're in a high-speed spacecraft, all of your coordinates now will not be x, y, z, t. It'll be x prime, y prime, z prime, t prime, meaning the prime not being a derivative, but meaning the prime indicating these are the coordinates in the spacecraft, what we call transformed coordinates. And it's actually not very hard to maybe conceive of what it would look like. And so let me just scroll down. Text commands. Okay, I'm going to grab this. So thankfully, there's a lot on the Peaceful Science website that's bright. And where is this? Latex. Go new line, new line, new line, new line. All right. And Damien asks, okay, if the Earth is stationary, just the math change, or is it possible the Earth is stationary? I really don't understand the math, but I get it can be brought in human terms. The form of the math, okay, so great question. Remember, the Earth is rotating about its axis, and then it's orbiting the sun. So technically, it's not stationary, but let's just suppose it's stationary. And then you have a very fast spacecraft that takes off from the Earth, and its velocity is so much faster than the Earth. We would just kind of model the Earth as being stationary because that spacecraft is really boogieing. And so Damien asks, is the Earth stationary? Does the math change? And the answer is no. No, not as far as electromagnetism and the way a lot of the machines on the spacecraft work. And if you think about it, that's a really nice property, because it would be really bad. I mean, just think about this just from a standpoint of your own personal experience. If you've ever ridden, well, you've definitely, I'm presuming, ridden in a car. If you've ridden in an airplane, it's really nice, for example, that, I mean, I think when I was a little boy, I was like, okay, we're going really, really fast. And if I drop the ball inside the airplane, would I expect it to kind of move to the back of the airplane? And you notice it doesn't. It's like everything inside the airplane behaves as if you were stationary, unless you're feeling turbulence. But let's say you're having a nice, smooth flight. You would not know that you're actually moving. Everything feels the same. So inside the airplane, all the math is the same as if you're on a stationary planet. I hope that helps. So does that sort of make sense? Your experience, you don't feel it. Now, granted, when you're an astronaut, you're out in space, there's weightlessness. But in a lot of respects, the better model is kind of like when you're on that airplane and you have just an incredibly smooth ride. Hypothetically, you would think you're stationary on Earth. So when when the flight attendant's pouring a drink into your cup, it's as if you're stationary, aside from maybe the shaking. And so what we're trying to describe is how much can we preserve that is of the math that is the same way from a stationary object, a stationary context to a moving context. Well, the thing if you're going to preserve the speed of light and also like the way your electronics works, like the capacitors and your motors, etc. Yeah, that's exactly it. The cup don't spill over. You end up coming up with this funny conclusion that either the clocks or time has to flow differently. It's not brutally obvious. But when people started to come to terms with this, they began to think, this is really weird. This is really weird. The time would have to flow differently. So let's say your airplane, and say there's some way that you could simulate gravity being the same. If it were going very close to the speed of light, a day would be inside the airplane as 1,000 years on the stationary Earth. Now, this is all very hypothetical, but I'm just trying to illustrate. And you're like, it doesn't make sense. But the math is trying to show that this is actually what's going to happen. They began to think about this, and it was very troubling because it's like, no, that can't be. That can't be. And they couldn't run away from it. So what this equation is saying is, let me just show it again here. You can barely see, you see this x squared, and then you have this x and then this little tick mark. That means we call that x prime squared. So if this is the stationary Earth, the way the math works in the stationary Earth, in the spaceship, it looks about everything relates, it has the same form, except you're using just ticks. But if you're inside the spaceship, it'll look like just X, Y, Z, and T. And in the spaceship, it'll look kind of the same form. So the mathematicians will say this has the same form, and that's what we want. The difference is that the tick marks indicate how, like for example, how different the time would flow between the stationary Earth and the spaceship. We would compare our clocks, the speed of our clocks with this t, to the speed of the clocks on the spaceship with the t prime. But within the spaceship, everything would look normal to us. And this is what the equation says. To get down into the math as to why that's a little bit nasty, but that's basically what the equation says. And so what we're trying to derive, we have to start with this and then show that when we're in that fast spaceship, we would get this. And that's where the math gets really a little ugly. And but this has been a good, this is great to have gone through this because it's actually helping me to understand this myself better. So now let me get back to my equations here, and I have to go through this because I have so much here. Okay. I'm going to get rid of some of my extra windows. I'm going to get rid of the Maxwell's equations. And this document is now useless. I have to figure out how to better way to represent this. This has come. Here's the math jacks. I can get rid of this. And online. Okay, I want to keep that. Get rid of another window. I have so many windows open here. All right, getting better now. Okay, so now we'll walk through some of the nasty math, and Dr. Bursha solved some of the was able to get through some of. So now this is just the ugly calculus part of this, and I got through most of this. Dr. Bursha helped me recover a formula I'd long since forgotten, and it's in here. So okay, so we talked about the Laplacians. And so this is the Laplacian here. And then this is just a regular second order derivative. But if we take out the b's or the psi's and we collect it, we would call that a D'Alembert. So let me see if I can show you what I mean. So we started with, and oh, by the way, that relates to the character. Hang on one moment, guys. I got to explain something. See if I can find it here. That relates to the thumbnail. So we had this thumbnail. And you're like, why did I make that the thumbnail? Well, there's this thing, I don't know anything about Yu-Gi-Oh! It's something like a game, Yu-Gi-Oh! And they use these cards. And there's this creature called the D'Alembert. Let me see. It's not the best picture. So this is his weapon here. That's his hand, his arm. That's his little head. And then all his armor behind him. And maybe he has some, are those jets behind him or something? So that's the D'Alembert character. And the word D'Alembert comes from physics, named after D'Alembert. So now I'm going to derive the D'Alembert that comes from the Laplacian, comes in part from the Laplacian plus a little bit more. So let me get rid of that. Okay, so we've already shown this. This is the Laplacian here, and then the second order derivative. I'm trying to show how can I derive the D'Alembert. This is going to be painful. Let's see if I could do this. So because I said this is going to be about D'Alemberts. I'm going to have to modify this equation by hand. So is going to be a little painful. So I'm going to just take the electromagnetic equation, the electromagnetic wave equation. So this is one form of the electromagnetic wave equation. I'm going to frame it in terms of a Laplacian and then a second order partial derivative in the time with respect to time. I'm going to frame it in terms of a DL inversion. Let me see if I could do this. So this will be, hang on, I think I can pull this off. Give me one moment. Okay, so I'm going to remove this. Okay, this is going to be easier than I thought. This is going to be scary difficult. It's not too bad. All right. The first equation here, this is another way of stating that same equation. So what do we, where we make all of this as an operator operating on this wave, on this field, which I'm calling the psi field. It could be anything E or B, electric, magnetic, doesn't matter. This operator here that I just concocted is called the DL inversion. So you could frame the electromagnetic equation like this, or you could frame it in terms of the DL inversion of that field. And just to make sure that I got this right, I'm going to look it up in Wikipedia. It's the box operator. Hang on. So DL inversion. Let me make sure I got this right. The DL inversion, they have all the signs backwards. Ugh. The operator is different. Okay. I have to redo. So I'm going to have to redo this. Better now than later, huh? I can make this negative since this is a 0 here. And so now I know I'm going to have to correct all this. All right. Okay. So let me save this for now. I'm going to collect this into my collection of equations. And now I'm going to have to just change the sign of everything. Ugh. Okay. So let's change the signs of everything. I'm going to subtract this from both sides of the equation. And that will just flip the signs. This is equivalent, but it's just going to look a little different than the way I laid it out. So this should be, I need to put something up in front. So I will do this first. Hang on, can I undo this? Sorry, apologies. Okay, try this again. Okay, what I did here is this system of equations is equivalent to this system of equations. You just have to do a algebraic manipulation. And so this here, this term here in the brackets, that's the DL-Bursha operator, according to Wikipedia. Let's confirm it. Partial. Okay, let's compare that I got this right. Biology is so much easier, guys. So I have C1 over C squared partial, second order partial with respect to time, and then second order minus the second order partial with respect, partial derivative with respect to x, and then with respect to y, with respect to z. It's called the box operator. And we have specialized notation that uses tensor notations and general relativity. I'm not going there today. This is a funny symbol. This upside down triangle is equal to the Laplacian. That's something I'm not acquainted with. So we could also express this as this Laplacian operator here. Okay. So now I got this better. I'm going to save this. I've gotten the math a lot better now. Much better. So now I'm in conformance and I'm not looking so backward. Okay. Yeah, this is mathematical physics. It's tedious. Biology is so much easier. Okay, so now I framed this in terms of the DL-Bursha. I'm going to have to redo all of my equations because everything's backward the way I laid it out on Peaceful Science. So now let's go back to the DL-Bursha. Okay, so this is a backward DL-Bursha, and I'm going to have to fix that. So this is where it gets really nasty. Okay, now I'm going to do, this is a derivation I made. This is still valid. And let me gather this and show it. Here. All right, I'm going to wipe the slate, so to speak. Let me save this. I'm going to wipe the slate here. So I'm going to focus on this second order derivative on this psi field here. Second order derivative on the psi vector field. What would that look like on the equation for the psi vector field? Okay, second order derivative on the equation that describes the psi vector field. And so let's look at that. This is what it would look like right here. That's just simple second order derivative on the equation that describes the psi vector field. That's just the notation for it right there on the left-hand side. Now, if we're transforming it, if we are taking what it would look like in a transformed coordinate system. So in physics, we have transformed coordinate systems. So let's say you're stationary and you have this fast-moving spaceship airplane. Now, this is all hypothetical. You have the coordinates inside the airplane and the coordinates on the stationary Earth, stationary position. So you have X, Y, Z here, and then you have kind of the X, Y, X prime, Z prime, X, Y, X prime, Y prime, Z prime, T prime coordinates in your spaceship, X, Y, Z, T in your space, in your stationary Earth position. Again, these are all hypothetical, just to simplify. You can relate. I'm trying to see what this means. If you're trying to describe this using X, Y, Z, so you're trying to convert the X, Y, X prime, Y prime, Z prime, T prime, and describe it in terms of X, Y, Z, T. So you're trying to describe the spaceship's coordinates using the Earth-based coordinates. So you have to do some math to do that. This is well known in calculus. It's just tedious and agonizing. And then you have to do, when you're relating the derivatives between the two coordinate systems, you have to use these ugly chain rules. So we've done this in calculus. The chain rule in multiderivatives is just, again, nasty. But it would have been nice if we had been able to do what we call simple Galilean transformations. And without getting into it, if you applied the Galilean transformations, and I'm sorry to throw just another technical term out here, but just for the interest of time, and you could tell it's already almost 2 hours. The Galilean transformation will not result in the preservation of let me see. You will not result in the preservation of this D'Alembert form of the wave equation, the electromagnetic wave equation. It would fail. You need a transformation of coordinates relating x, y, z, and t from the earthbound coordinates, to the spaceship coordinates, the Earth coordinates to the spaceship coordinates. The Earth coordinates will look, if we could hypothetically say the observer on Earth, in his coordinate system, time would look like it's slowing down inside the spaceship. That's a consequence that if you want everything inside the spaceship to behave normally, quote unquote, and he wouldn't feel that his clock is slowed down, he would just feel like a regular day, 24-hour day. Whereas on the Earth, observing what's happening up there, hypothetically, if that could happen, it would look like he's aging very slow, where a day in his time looks like 1,000 years here. And then 1,000 years here looks to the spaceship's perspective to be one day. And that, again, that's the consequence of everything we talked about in like the first hour. And to do that, Lorentz figured out how to do this. And there's a whole history on this, how he figured out this transformation. And it's called, just for reference, there is this Wikipedia article that talks about the history of the Lorentz transformation. This led to the Nobel Prize. Okay, we are talking about Nobel Prize winning work. So I mean, the math is just going to be just Nobel Prize winning math. This is par excellence math. It began with Voldemar Voigt, 1887. He developed a mathematical transformation in connection with the Doppler effect in an incompressible medium, being in modern notation. This is incompressible medium would be like water. So the sound wave traveling through water, he came up with something that looked very much like the Lorentz transformation. So now I'm going to describe the Lorentz transformation. The Lorentz transformation, and let me now go to my notes. The Lorentz transformation does this to the x, y, and z coordinates. So I'm in the process of redoing all of this to make it more compact and polished. Okay, here it is. So that's the transformation. I'm trying to look at this. I'm sorry. I got to look at the Lorentz transformation. This is agonizing. Okay, here it is, right here. This is the Lorentz transformation. So and T prime is gamma T minus Vx over, okay. So what you're seeing me do, guys, here is I'm trying to make a more polished presentation of some really disconnected ideas. I'm revisiting this. So this is Lorentz's transformation, that if we're going from the x coordinate being the Earth coordinate and the x prime being the spaceship coordinate, you would relate the two coordinate systems this way. And let me try to think about this. Okay, so normally, if I believe, I'm pretty sure of this, you would not have to, minus some offset constant. You could just use the Earth coordinates and use them in the spaceship coordinates. Would that be right? There's a Galilean transfer. I have to go back and look. I think the Galilean transformation would not. Okay, a Galilean transformation would be, you would not have the gamma term. It would be just x minus vt. So the coordinates would change. Okay, that's it. All right. The Galilean transformation, you would just, if you had a spaceship traveling, okay, you had a fixed x, fixed y distance. Well, just strike that for the time being. The x coordinate would, in the Galilean transformation, the x coordinate of the spaceship would be changing here on Earth as we observed it. In our coordinate system, the spaceship is changing like x minus vt. X minus some, so we would take our x coordinate, and then however much time has passed, we would subtract minus vt to come up with to relate the two coordinate systems. If you did that, you would sacrifice you'd not be able to preserve the behavior of all the machinery on the spaceship. Since we're assuming that the behavior of the spaceship, the machinery on the spaceship, laws of physics are the same for the spaceship as they are for there on Earth, you have to apply this transformation. You have to apply the transformation. So you have to apply it. We're going to show why. So if you put this transformation in there, then you can Lorentz realized if you apply this transformation, you can preserve the laws of physics in both reference frames. Okay, I'm fumbling through this. The next time around, God willing, it's going to be better. And he also deduced that the clocks would have to change also based on the speed. And he put that transformation there. And so this is the transformation for the x coordinate. This is the transformation for the time coordinate right there. So let me grab that. Okay, so transformation for the x coordinate, transformation for the time coordinate. Now, we can actually take derivatives of this. We can take partial derivatives of all this. So we'll assume that x prime equals this, y prime, t prime equals this, and then for the x, the y and z, y prime equals y, z prime equals z. I don't exactly remember how that worked. Z prime equals z. Okay, z prime equals z, y prime equals y. All right. Now we can take the partial derivative of x prime with respect to x. So partial derivative of x, if x prime is framed like that, and we take the partial derivative of that, we'll get gamma. And just to show that, Wolfram alpha. You could do this in your head, but if you want to, if we want to do this, double check this, we're going to go to we want algebra, calculus. We want the derivative. The derivative of gamma x minus vt and v dx let me see if I could do this right. I'm trying to do this right in Wolfram alpha. Let's look at examples. I want examples of a derivative. Come on. Okay, so let's see, gamma. Let's try backslash gamma. It's using a gamma function. I know maybe it doesn't like that. Okay. All right, better. Okay, it wants a backslash gamma. So d dx, d dx. I'll click equal. Okay, that's better. All right, so now let's look at d dx. So gamma, and then we have x minus vt. Okay, x minus vt. Let's see what we get. Should be just, that is so wrong. I don't want the gamma function. Dang it. I don't want that gamma function there. How about just plain old g? See what happens. Okay. I don't know why it's not liking this. Um, I'm trying to find symbols. They're painful. I need a symbol. Okay. Okay. d dx of that. Why is it giving me this blasted? This is ridiculous. Try this. See, this is really obnoxious, guys. I should be able to type in gamma and get gamma as a result. This is really bad, guys. It's not supposed to do this. This is pathetic. Gamma is the gamma. I don't want the gamma function. I just want gamma as the there. Okay, this is obnoxious. Okay, now I learned something about Wolfram that I really don't like. This is painful. I'm just going to put a G here or something. I don't want that blasted gamma function there. Let's see. Okay, so Wolfram is doing something kind of like what I really don't like. It's using gamma. When I'm trying to enter gamma, it's putting a gamma function. Obnoxious. Okay, we'll just have to do this by hand. I apologize for that. I learned something the hard way. And there is a bug here. I need to spray him down. I had to zap him. Okay. Goes to show Wolfram Alpha is not going to solve the problem. So we have to do this the old-fashioned way. We take the partial derivative of this equation, partial derivative of x prime with respect to x. We take then this formula, take the x prime versus x. So we start with this formula here. And we take the partial derivative with respect to x. You get gamma. The partial derivative of this with respect to t, you get gamma v. Let me see how that works. 0. Of x prime with respect to t, you get gamma v. Okay. All right. So here we're going to get all, you're going to get a whole list of these here. And just note, we're going to have to save this for future reference because we're going to apply a chain rule. Okay. All right. Sorry about that, guys. Okay, so let's look here. Going back to where we were starting, if we were going from one coordinate system, like say x to x prime, you'd have to take a chain rule, and it would look, I skipped a step here. Let me make this a little easier to see. I'll take this. That equals partial. I'm going to show what I mean. 1 second. This is so. And I just blew that up. Hang on. That didn't work. Made a mess of things. Hang on, guys. I'm sorry. Try this again. Frac partial partial. Look at that. That's okay. And we want left. We want the left bracket. Okay, we got the brackets there, left and right. And I want I'm going to take this and put it in there. Left bracket, right bracket. Okay, and I'm going to take the number 2 out. That. Yep, that's what I wanted. So let me save this. So this is basic calculus right there in terms of the second order partial derivatives. Yep. Okay, so I'll put this in my equation cheat sheet, my equation processor here. And so this, if we use the chain rule for partial derivatives, we get this. I mean, kind of using kind of the math of like fractions. You could see like the x primes would cancel out, the y primes would cancel out, and you would just have partials. Let's see how this works. Let me look at this. Get the partial of x. Trying to think. I don't know how this works, but this is just the accepted chain rule. So let's look at the chain rule for partial derivatives. All right, chain rule for partial derivatives. Let's look at Libre text. That's just a standard. Chain rule partial derivatives. Let's just do 3 variables. Okay, Okay, let's go back to this one. Make this bigger. Unfortunately, we don't have, I mean, one would have to translate all of this the way that it's stated here. And I'm just going to have to say, okay, this is where it's a little difficult to kind of uncoil and rewrite the symbols so that you could see that the way I rendered it here, this is the right way to state the chain rule in terms of derivatives. So let's, let me go here. This here expands to this. So if we wanted to frame this first order derivative in terms of the x prime coordinates, this is how you would do it. It's just a little ugly, okay? That's just the way it is. I don't know how else to say it. If we applied the rules of calculus, you'd have to go through the calculus books and be able to kind of decode what their symbols mean to translate it into the symbols here, but this is what it would look like. And so I'm just going to copy all of this now and dump it into my collection of equations. So I'd written this a long time ago. All right, so now we have that. And so what does this right here, this x prime x, what does that mean? And so now we go back to our Lorentz transformation. X prime x means we take the derivative of the right-hand side and we get gamma. So let's look at all of these. X prime x, x prime t. Okay, the derivative of x prime with respect to x, the derivative of x prime with respect to t, derivative of t prime with respect to t, derivative of t prime with respect to x. Okay, so x, hang on. Let me see what we need. Going back to this, derivative of x prime with respect to x, y prime with respect to x, z prime with respect to x, and t prime with respect to x. So let me see what I have listed here. I don't think I have it in the right order. X prime. Okay. I have to complete the list. I had the complete list here somewhere. So I can arrange this. I'm going to have into a nicer PowerPoint so I'm not just jumping all over the place anymore. I had it listed here. It's been like 3 years since I've done this derivation this far. So, and after 2 hours, I'm about to quit. Okay. X prime with respect to x, x prime with respect to y, x prime with respect to z, x prime partial derivative, x prime with respect to t. So I'll show you how I did that. I'm going to have to do this. I can work through this a little bit better. So let's start with the Lorentz transformation. You know, John Harsman's a real jerk, honestly. It adds nothing to the conversation. He's an evolutionary biologist, doesn't know half of what he's talking about, and he's interjecting in my thread. It's really obnoxious. I'm seeing his comments here. Really ticks me off. Okay, now I have to look where that Lorentz transformation is. Then I can make a nicer presentation with all this. There's another guy I don't like is Patrick. Okay. So we have the Lorentz transformation. X prime equals gamma x minus vt. So x prime with respect to x, just do a partial derivative with respect to x, you get gamma. Partial derivative with respect to y, since there are no y terms here, you get 0. And partial derivative of x prime with respect to z, you get 0 since there's no z term here. And then partial derivative of x prime with respect to t. So there's no t term here, so that you can just, when you take the derivative of that, that's 0. You end up with just this t x prime with respect to t. I'm sorry, it's the derivative here. I'm sorry. You get minus gamma. When you take the derivative of this, x prime with respect to t, you get minus gamma v. Yeah, okay. So those are the 4 there, and we're almost ready to stop for now because we're going on almost 3 hours. So I'm going to collect these equations here, and I'll know how to collect this, how to do this the next time around. And I'm getting tired. I know you all are too. So there. Let me grab this here. And then I'll grab this. So this is just like a homework session. Then I'll grab this. Didn't want that. I really wanted partial with respect to z. And then this part here. Okay. Now I'll show where all this goes. we have these results here for the partial x prime versus partial derivative of x prime with respect to t and all these other terms. And how does this relate to what we are trying to do here? We can, all right, going back here. This is so obnoxious how this thing lays out. When I shift between one form and the, when I resize the windows, it just behaves funny. Oh, this is really obnoxious. Sorry, guys. Okay. Darn it. Why did it do that? Okay. When I shrink it, I want it to stay. I didn't want it to do that. See, when I shrink the size of the window, it just, I lose so much of what I was trying to present. Okay. So what am I trying to do here? Let's see if I could shrink this a little more. Okay, so you see this term x prime over x right there. I could substitute a gamma there. I could put a 0 here and a 0 here, and then a gamma v there. This is kind of gold right there, this little overlay. When you do all that, it'll simplify beautifully. It's going to simplify beautifully. And that'll be the topic. I need to try to get all of these slides a little bit more compact, and we can proceed. So part 2 will be just going through some of this, and I hope I can have better rendering and better slides, because the way I'm going through this right now, I'm actually reviewing it as I'm doing the homework, doing the work, and it's just all over the place. But it helped me teach this a little bit better, just kind of thinking in the open. So this is kind of an editing room floor. So this is really painful. Okay. So the reason I'm kind of doing it with these equations in LaTeX, if I were writing this, it would just look ugly. And you need a blackboard that's just walls to get it all to connect. I mean, maybe that's possible. I might have to look at some software where we could do this. And I have to kind of conceive of how we can just lay this out. But it's helpful. What I'm thinking about doing is writing an educational paper where we get the students to do some of the derivations in pieces, as I'm doing here. And even if they don't understand the physical meaning, at least they're getting experience learning how to apply kind of the rules of calculus to each of these parts if they're doing multivariate calculus. So the reason I think this is going to be just maybe a useful exercise is a third semester calculus student can actually be able to demonstrate Nobel Prize winning math. Now, he may not understand all of it, but it'll at least let him feel that now he's really accomplishing something of really very high level. Some of the math that had driven kind of a breakthrough in physics. And so it's not that each of the steps is inherently that hard, but there's just so many of them. Because at some point, the equation, I'll show you what it ends up looking like at some point when one actually goes through it. It just looks gruesome, just because it's so big. But the individual steps are not that awful, but collectively, because it takes so long, it ends up looking like a monstrosity like this when you start taking all the pieces. And then you're just like, wow. But then it resolves into something simple and elegant at some point. And so I just needed to go through how this is working. So thank you very much, anyone that's still hanging around on this. Damian Martinez, thank you. God bless you. Oh, thank you. So thank you very much for the kind words. I need them. So anyway, this is where we'll have to leave off, because I've really kind of just stumbled through the explanation. It's been a long time since I've done the math. You could see me kind of struggling through it. And also some of my notes that were on Pitiful Science, on the Pitiful Science website. I'm having to kind of cobble them together. I was having problems with Wolfram Alpha, which was not rendering the derivatives correctly. I had to look up the chain rule, which was not, it didn't have the nice form that I wanted, so I have to derive that. I was having problems rendering latex onto the screen, and then all my notes were just all over the place. I did get to go through some of the theory and then try to understand all the coordinate transforms. And some of the cobwebs are starting to disappear now. So I think we're headed in the right direction for this, and eventually I'll have a better presentation. So how does this relate to the Christian faith? Understanding this relativity and how time can change depending on your velocity, it may indicate certain properties of space. If that property of space that alters the way the clocks behave, let's say that out there in space, light can travel faster. That would mean, if there's a 0-point energy, or what we call the ether, out there, if the energy density is lower, light can travel very, very fast. It would solve the distant starlight problem of young Earth creationism. We might have a means then of confirming the genealogy of Jesus Christ. The genealogy of Jesus Christ, as in confirming it, the literal reading of it, that the Earth and the universe are young. So this is where all this is leading. I maybe should have started this out. The quest of doing all this agony and bearing this cross is to find evidence of a literal reading of Luke chapter 3. And if we can find evidence that supports a literal reading of Luke chapter 3, that would be evidence for the Christian faith. So Damian Martinez, thank you for bearing this cross with me, and God bless you. Let me just say a prayer for everyone and for this project and the visitors in this channel. Heavenly Father, science is across to bear, and the math is certainly across to bear. It could be months, years, decades of agony to just get a little bit closer to finding evidence of a literal reading of Luke chapter 3, and therefore evidence for the Bible being true and evidence for the Christian faith being true. Please bless our efforts to learn and study these things. And even though we only see through a glass darkly, things are getting clearer with each day. Help my work and the people here in this channel to move the discussion forward and get clarity, and that we can find evidence for you that you've hidden throughout the ages and now revealed in these end times. We glorify and honor you, Lord, in the blessed name of our Lord and Savior, Jesus Christ. Amen. And please be with Damian Martinez, especially as he's been so kind to support me during this time, and everyone else that has visited this channel today and also through recordings. We offer this prayer in the name of our blessed Lord and Savior, Jesus Christ. Amen. God bless you all. And I'm going to have the closing credits now.